And static correlation for H2 means the dissociation limit. And of course, what I'm trying to illustrate is the problem with the dissociation limit for a Hartree-Fock wave function in general. But it's most easy to discuss it for H2. But I mean, it's an example for the general case. So if we are in the dissociation limit or close to the dissociation limit, then the overlap integral is getting close to 0. So in the dissociation limit we can set the overlap integral to 0. So our two molecular orbitals are then sigma g just 1 over square root 2 to chi a, is it capital? Yeah, chi a. The atomic orbital, the 1s function on hydrogen A plus the 1s function on hydrogen B. And the sigma u molecular orbital is then chi A minus chi B in the dissociation limit. In the dissociation limit we also have no interaction. And that means that the orbital energies sigma g and sigma u are then the same. If there's no interaction between the electrons, then there's no reason why the orbital energies of those two orbitals should be different. So they are the same, so we have a degeneracy and as said, the degeneracy is where we have static correlation. Now, the two-electron wave function, in that case, how should that look? How would you? I mean, it's a singlet, so I should have a singlet wave function, spin wave function, alpha beta minus beta alpha. But how would you say should the orbital part look like in the dissociation limit? The hydrogen molecule dissociates to what? Hydrogen atoms. So I should have, where should the electrons be? Yeah?
One on each.
One on each. So I should have that one electron is in chi A and one electron is in chi B. So I should have something like chi A, chi B, electron 1, electron 2, but I'm still not allowed to distinguish between the electrons. So I guess I should have also the other option, that they're just interchanged. That would be appropriate wave function to have. One electron A and one electron B. Should be. Now let's look at our Hartree-Fock wave function. How does that look like? Well, the Hartree-Fock, still in the dissociation limit. That's obviously sigma g, and one comment first. Let's ignore the spin. We ignore the spin part because it has nothing to do with spin. So just write the spatial part. So the Hartree-Fock wave function, and therefore I don't write the equal sign, but just semicolon, is then sigma g for electron 1 and sigma g for electron 2. That's still the same. They're both in the sigma g. But what is that? Well, sigma g, that's 1 over square root, 1 over square root, so that's 1/2. And then I get chi A plus chi B. That's this one, sigma g. So that's chi A of electron 1, chi B of electron 1. That's for electron 2, the molecular orbital, but that's still chi A plus chi B. And then times spin function. But if I write that out, if I multiply that out, I get 1/2, and then I get chi A for electron 1, chi A for electron 2, plus chi A chi B, that's this with that, plus chi B chi A, that's that, and then I get the chi B chi B. So this one, that's this one. That's the proper wave function where I have a dissociates it's in atoms. But that and that together, what is that? What kind of situation do I have here? Yeah?
We have 2 electrons on each, so we have ion.
Right. I mean, this corresponds to H minus, H plus, if that's A and that's B. Here, nucleus hydrogen atom A has 2 electrons, and B has nothing. And this is the opposite. This is plus for H and minus for B. So these are ionic wave functions, or an ionic situation, which is completely wrong. When a hydrogen molecule doesn't dissociate in 50% atoms and 50% the 2 different ions. And you can see, I mean, there's of course a spin function, but since we have the overlap is 0 in the dissociation limit, this is really 50% of the wave function is ionic, the Hartree-Fock wave function. So the Hartree-Fock dissociation limit is fundamentally wrong. It's the wrong picture which comes out, because we get a mixture of the correct one in atoms and 50% the wrong one, where we get ionic wave function. And that's really a static correlation problem. We have the wrong electron configuration here, or we have something mixed in to 50%, which is the wrong one. So how can we solve that? How can we solve that? Well, it's a singlet wave function. So we need another configuration to mix in. We have to make not a single determinant, one configuration wave function, but we have a multi-configuration. In this case, a 2 configuration wave function. Solution. 2 in general, multi-configuration wave function. So we make what is called configuration interaction, CI, configuration interaction. We write a wave function up which is 1 over square root 2, the Hartree-Fock minus this double excited determinant. And if we do that, in the double excited determinant, we had twice sigma u. You can see there's a minus sign in here. So basically writing this out, is going to, if I do that for the double excited determinant here, I get a minus sign there, I get a minus sign there, which means I get a minus sign here and a minus sign there. So if I take the Hartree-Fock minus that one, what I end up with is then 1 over square root 2, and then I get chi A, chi B plus chi B, chi A times the spin function. So here I get the proper wave function as I should. I get one which dissociates in the atoms. So for the hydrogen, just by adding a second configuration, I solved the problem of the wrong character of the wave function, the wrong qualitative character. So here, the interaction of two configurations and multi-configuration gives the qualitatively correct wave function. It dissociates correctly into atoms.